Okay, welcome back, everybody. So today we continue discussing supervised learning. So the first part, as I said, is going to be on supervised learning. We discussed a few supervised learning methods, including k-nearest neighbors, naive Bayes. Today we are going to discuss another supervised learning method called decision tree. As always, if you have any question, either raise your hand or post to the chat, and Daniel will alert me. And if he doesn't, I mean, some of your questions will be answered, but if not, he will stop me and I'll answer the question. Okay, so let's move to today's topic, which is, as I said, decision trees and maybe some extensions of decision trees. So again, just to orient us, we are talking about supervised learning. Within supervised learning, we are still discussing classifiers. We said that's not the only supervised learning approach. There is also something called regression, and we'll get to that actually next week. But today we are still discussing classifiers. And within classifiers, we divided the set of classifiers into three large families. So these are not individual classifiers. Each family has a lot of or can have multiple classifiers, but we generally divided them into instance-based classifiers. We showed an example, k-nearest neighbors. We had the generative classifier, which is naive Bayes, which you can generate new instances once you learn the classifier, and also classifiers that usually rely on the Bayes decision rule. And now we are moving to something called discriminative classifiers. And in fact, most of the, I would say all of the classifiers we are going to talk on from now on, or we are going to talk on later in the class, including logistic regression, support vector machines, and of course neural networks, are discriminative classifiers. These classifiers, unlike generative classifiers, do not necessarily assume a probabilistic model. Sometimes they do, but they don't assume a generative model. So generative means that once you know the model, you can generate new instances. Discriminative classifiers either do not assume any probability, like decision trees that we'll talk about today, or if they do use probabilities like logistic regression, they use it directly. So they try to directly predict P of Y given X without using Bayes to predict P of X given Y. So they don't have a way of learning the distribution of P of X given Y. This is why they are called discriminative. They are trying to find just the value of Y without any attempt to model how the data was generated. And these actually are the more successful or more, well, at least the current most successful algorithms are discriminative classifiers. So obviously you've all heard about neural networks, and they are obviously very, very successful and powerful, but decision trees, and more importantly, extensions of decision trees are also very, very useful. And in some domains, they're even better than neural networks. So discriminative classifiers are actually, I would say, the most successful, at least nowadays, in terms of and the most used classifiers as well. Okay, so what is a decision tree? So a decision tree is a very intuitive classifier. If I had to guess, I would say this is the classifier people have used, or the first classifier people have used even before machine learning or AI, I guess a century or 2 centuries ago. You could easily construct a decision tree. Maybe it wouldn't have been as good as what we can do today, but it's very intuitive. Okay, so before we, so I'm going to do something slightly different. Before we go into the theory and algorithms and explanations of how we design a decision tree, let's do a decision tree, a crude one. So it's not going to be the optimal decision tree, but it will provide information on how decision trees look and what they do. So for that, I'm going to do a poll. So this is not a quiz now, it's going to be a poll. So I'm going to open the Piazza. Before I do that, in this case, we need a training set and a test set. So I'm going to ask everybody, okay, so everybody whose last name, okay, last name starts with R, S or T, okay? R, S or T. I just looked at the roster and it seems like this is like 10% of the students. So anybody whose last name starts with R, S or T, don't fill up the poll. You will be our test set and you will do another thing at the end, okay? But for now, you sit out, and everybody else, I'm going to open 4 questions. Please answer them. As always, these are completely anonymous, no grade. I mean, this is just some questions about you, but they are anonymous. I have no idea who is who, so feel free to answer, and you will see it's not related to any issue. So, right, so I'm going to open, so open Piazza. I'm going to release 4 questions there about your phone, your cell phone, and we'll try to build a classifier based on that. Okay, so I'm releasing the questions. And again, if your last name starts with R, S, or T, please do not complete these, or don't fill up these quizzes, these polls. So, right, so Apple is going to be pretty happy with the results of this poll, it seems. But hopefully we can do some. Oh, no, there is some cases where it's not dominating. Good. So it seems like a PhD students. No, that's actually not working well for us. Yeah, this is the best one, I would say. So male are more evenly divided. Oh, good. Okay, so we are looking for something that will distinguish a iPhone from non-iPhone users, and it seems like citizens have more, on average, have more phones, have more Androids, at least slightly more, and people who are not citizens have more. Oh, that's also true for STS. Good. Okay. So let's build a decision tree as follows. So we have citizen, we said STS, and then I think which one is. So we're going to use, we don't have to use all of the questions, but let's build a decision tree and see. And of course, this is not going to be optimal because I didn't ask for the relationship. We'll get to that, but let's start by building a decision. So a decision tree is basically a set of questions. Each one has either 2 or more answers. For now, we will assume it has 2 answers. And each one sends you either to another question or to a decision. So let's say that we are asking whether the first question is, are you a citizen? If you're a citizen, then I can say, so this is, let's say, 1, this is yes, and 0, it's no, okay? So this is the first question. So I'm asking whether you're a citizen. Now I can ask another question, whether you are an STS student, okay? So let's say if you're not a citizen, I'm going to predict this. So this is something called an internal node. It has a question. And then there is terminal nodes. Terminal nodes are the basically the decisions. So I'm going to say iPhone here, okay? So if you're not a citizen, I'm going to predict, the tree will predict that you're going to have an iPhone. If you're a citizen, I can ask another question or I can make a decision. In this case, I want to ask another question, whether you are an STS student. If you are an STS student, I would say you have an Android phone. And if you are not, this is if you are a citizen, I would say you have an iPhone. Okay, so this is a full decision tree. Now, again, this is not the best way to learn it because we don't really know what's the relationship between citizen and students and STS students from the questionnaire, but definitely this is a reasonable decision tree. And what the tree, again, what the tree says is that now you're a new sample, you're a new test case, maybe one of the R, S, and T students in the class. You look at the tree and you start going according to the questions. So the first thing you ask yourself is, am I a citizen? If yes, you're going to the right. If not, you're going to the left. If you're not a citizen, then the prediction of the tree is that you have an iPhone. If you are a citizen, then you have another question to ask yourself. Are you an STS student? If yes, going to the left. Then the prediction would be Android. If no, they're going to the right and the prediction will be that you're an iPhone. Okay, so this is the prediction that we are making. And now I want our test set to do the poll that I'm releasing only the R, S, and T that didn't do the actual iPhone. And let's see if we got them correct. Please fill in the the poll that I opened up, which is called a DT test. If you're RS and T. So check if basically, you should see, I think, my screen, right? So you should see R3, and if R3 got you correct, just, so, if you are RS and T, just use the tree and let us know if we got you correct or not. Let's see if the method worked. Not good. That's it, only 4 people, RS and T, there should be more. Now, if we have 80, I would imagine at least 8. Good, we're doing better. Okay, good, so 8 is more or less what I expect. Maybe we have, even better. Okay, so yeah, so let's see the results. So our decision tree wasn't, good, last minute change. Our decision tree worked, and it got more correct than incorrect. It's not, of course, optimal, but at least it's very simple to write a decision tree, and hopefully very clear what the decision tree is doing. The big question for us, or the big challenge, is what are the questions that we should ask and how we should assign the labels. But other than that, when you see a decision tree, right, if I show you a decision tree, it's very clear what the decision tree is using and how it's using it, right? Unlike, for example, if you look at a support vector machine result or neural networks, it's very hard to understand what each of the internal nodes is doing. But in a decision tree, it's much easier to understand. That's why it's very popular, especially in domains like sciences, where you care not just about the accuracy, which is something we care a lot about, but also about explainability, which is very hard to do in some of the other machine learning. So decision tree is very good. Again, this was very informal. So the rest of the lecture is going to be about how to do this formally and accurately. But I mean, unlike other methods, which, I mean, let's say support vector machine, there's no way for me to show you this informally, only through formal. Decision tree is actually something I can show you informally, which is, I think, nice and also makes it very intuitive. Okay, so this was just an example, and let's go a bit more formally, as I said, about what is a decision tree, how we construct a decision tree, which questions are we going to ask, and how we are going to use it. Okay, so this is the lecture. Okay, so decision trees, as I said, are easy to understand. The nice thing about decision trees is that in addition to being very intuitive, they also work well. Decision trees themselves actually do not work amazingly well. They're not bad, but they don't work very well. But pretty simple extensions of decision trees work very well. And we'll get to that later in this lecture, or maybe next time, we'll see. Okay, so we built a decision tree, but now let's discuss this a bit more formally, right? So this is the structure or the graph of a decision tree. A decision tree has a set of nodes, internal nodes, that these corresponds to questions on the attributes. So basically, these are the features that we have. For example, which school you're going to, what is your degree, whether you're a citizen or not, what is your gender, and we can have, of course, other features. These are the inputs for our samples. And these can occupy internal nodes, and there is answers, yes or no, depending, or there could be, I mean, this is for binary, but there could be, right, there could be multiple questions. For example, whether you're in the School of Computer Science, School of Engineering, or School of Sciences. So this would be 3 different answers. It doesn't have to be, a binary question necessarily. It could be from multiple answers. We will get, I'm not going to talk about continuous value, we'll get to them later. For now, we assume that all the features are discrete, okay? Binary or discrete. So this is the questions that we have, and these correspond to internal nodes, to questions, and then the leaves, basically the terminal nodes, corresponds to the prediction of the decision tree. So this is the classification. Do you have an iPhone or you don't have an iPhone? Okay, yes or no? And edges are basically the answers to the questions, which feature we are going to use. Okay, so this is how a decision tree looks like, and you can have, 1 layer, you can have 2 layers, you can have 10 layers, you can have a lot of layers, and we'll get to how many layers later. But you can have a lot of layers in the decision tree, so you can ask a lot of questions one after the other, and then make a decision. Okay, so how do we build a decision tree? I'm going to use an example based on the Netflix challenge. So a long time ago, Netflix, I mean, they're still very interested. So Netflix, of course, the goal is that you remain signed in. They don't want you to leave. So they want to be able to recommend good movies for you. And for that, they have an extensive database of things that you liked, and they want to use it to predict what is the next series or movie or whatever that you like. And the goal is to predict your interest in a specific movie or series based on your previous history of watching series. And for that, they have they have a lot of data. And our goal would be to build a decision tree to predict whether people would like a specific movie or not. Okay, and this seems like it's not a theoretical thing. People are using it. Netflix actually had this big competition a few years ago to try to improve their algorithm. And they gave, I think, a few $100,000, maybe $1 million to those that succeeded. Anybody knows, by the way, of another company that did such competition that basically gave out a database and asked people to improve their algorithm? That's actually ended a year ago. To make predictions. Anybody heard about these type of competitions? But this one actually was $1 million competition. You could have won. Not Facebook, not Kaggle has a lot of competition. No, keep posting. No, I don't know about Hulu. As far as I know, Hulu didn't do it. Great, Jason Xu. I don't know who it is, but Jason Xu is correct. Zillow is a real estate company that, if you go online, gives you a prediction. They call it Z-estimate, I think. It's their predictions about how much house should cost, basically your house, or if you want to buy another house, how much it would cost. And they have a big interest in getting it right, because if they don't get it right, let's say, they tell you that your house is worth more than it is, then it will just sit on the market for a long time. And if they tell you that it's less, then you might lose money. So they're trying to improve their algorithm, and they released so they have already very good predictions, and they asked other people to, and that data, I think, is available on Kaggle. And this was a competition that people have participated in, and with a very big prize. The improvement was actually pretty small. They already had a very good algorithm, but people were able to improve it, and someone did win, or some group won the prize. It turns out, by the way, that the winning strategies are not really those that came up with this amazing new classification algorithm. That doesn't work in real life. What does work is a very manual engineering of how different things are put together. So a lot of different types of classifiers put together, and we'll get later in the class about one idea of how to do it. Okay, but generally these type of competitions happen from time to time. It may be interesting to follow. But we are going to focus on the Netflix competition, which was a few years ago. So let's say this is the database that you have. So this is the data set. So this is the features, the type of the movie, and you can see we have more than 2: length, director, whether it had famous actors, and this is the label, whether I liked it or not. And our goal is to build, using this data set, to build a decision tree to predict this label. Okay, that's the goal. How do we do it? So these are called attributes, or the features, and this is obviously the label, the prediction of the cluster. So this is the algorithm for building a decision tree. That's it. It's a recursive algorithm, but it's very compact, right? I mean, you will see for other algorithms, we will have to work a bit harder than just writing it in a pseudocode. But this is basically the algorithm for a decision tree. The algorithm gets as input 2 values. One is the number of samples, n. And A is basically the samples that we have, and A is the set of attributes. Okay, attributes, we said, are the features that we have in our data, or for our data. Now, the first thing is whether we want to create a terminal node. So if empty A if we don't have any more attributes, and we'll get in a second to how come we won't have any more attributes. But if we don't have any more attributes, if the attributes entry is empty, or all the samples have the same label. So we got to a point where all the samples are yes, all the samples are no, then that's it. We don't need to ask any more questions because we know that for all of these samples that we have now, the answer is yes, or the answer is no. So that becomes a leaf. And the class is going to be either the class that is the class of all of the samples, or if we have an empty set, then the majority class. Okay? So this is called a leaf node. Otherwise, basically, otherwise means that we still have questions we can ask because we didn't use all the attributes. And also, not all the samples have the same label. Otherwise, we want to ask another question. We want to ask another question to split the samples such that some samples or the yes samples will go to one side and the no samples will go to the other side, and then we'll get a perfect decision. Okay, so how do we do that? We do that by finding the best question to ask next. So this is, again, a recursive algorithm. Recursive means that we build the first question, and then we ask the second and the third and the question. And the question is, what is the next question we want to ask? And we find the best attribute. How do we do it? That will be the rest of the lecture. But basically, that's the goal of the decision tree learning algorithm, to find the next best question. And once we do that, we split the samples based on that questions. So 1 second, I will answer. Iho, I will call on you in a second. So once we do that, we split the sample into two sets. One is the set where the answer to the question that we selected, which is this small a, is yes. This goes to one side. And the other is a set where the answer to this question is no. And we do something else. We remove, this is the recursive call, we remove from the set of attributes the attributes that we asked the question about. So for example, if I ask the question about whether you are a US citizen or not, I'm not going to ask this question again. Why? Because everybody on one side already has the same value for this, and everybody on the other side also has the same value. So asking this question will not separate the samples anymore. So this reduces the size of the attribute set, of the feature set, for the next call. And as you can see, it could be that at some stage, A will be empty, even if we start with a bigger. Yes, Io, please, a question. You can answer.
Yeah, I have a question about selecting the best attribute. So it's not about how we select it. I understand that we'll cover it later. But if we select it in this way, like recursively, a step on step, iteratively, a step on step, do we have any kind of formal theoretical guarantee that there's like a sequence of selected attributes would be best in terms of separating our space? What I mean is maybe the attribute.
No, I understand your question. Oh, yeah. It's a great question. The answer is, not only do we not have a formal guarantee that this will happen, in fact, I can show you an example where this doesn't hold. So okay, this is a greedy algorithm.
Yeah, that's what I mean, yeah.
And it's a greedy algorithm. It means that it is not guaranteed to result in the optimal solution. You're absolutely correct.
Got it.
And the best example is something like XOR or something like that, where you can actually show that this wouldn't work. But so let me just repeat the question and the answer. So basically the question is, if we go along this line of selecting an attribute splitting, is that guaranteed to give us the optimal tree? The answer is no. In fact, you can give an example where this will not give you the optimal tree. And the other answer is that selecting the optimal tree is very hard. In fact, the number of combinations is exponential, and so this is a very hard, or NP-hard, even an NP-hard problem to actually find the optimal tree for all cases. So this is a greedy algorithm. There is no guarantee that it will find the best tree. In fact, you can show that it's not going to find the optimal tree for many cases, but in practice, it works well. And still, even if it's a greedy algorithm, we want to find the best attribute that greedily does give us good result. Okay, but that's a good question, and the answer.
Thank you.
Good. Okay, so again, this is about the algorithm. As we said, NL is the labels, and the best attribute is the thing.
So we had a quick question in the chat. What is L? Is it the leaves?
L is the labels. Okay. L is the yes or no labels. And basically that's what we are trying to get, right? So if all the labels, if all the answers are yes, or if not answers, if all the classes, if all samples are from one class, or all samples are from the other class, then you don't have to ask any more questions. You just say class 1 or class 2. That's one the meaning of L. So L in this case is labels. Good. Okay, great. Thank you. So let's move on. Okay, so as I said, the question is, even though we are dealing with a greedy algorithm, and because it's a greedy algorithm, by the way, there's lots of answers to best attribute, because there's no, as I said, there's no way to prove that this is going to be the best, because there are cases where this will not work. So the question is, what are good ways to find best attribute? Before we go into some formal ideas that people are using, or some successful ideas that people are using, let me just motivate this a bit more informally by saying that a good attribute is an attribute, a good question is an attribute where it separates the samples based on the labels, right? So most of the samples from class 1 will say yes, they will go to one side, and most of the sample, will say, yeah, yes to this question, and most of the sample of class 2 will say no and go to the other side. The problem is, if we have more than, if we have 2, maybe that's not so hard. We can just see how much, like if it's 5, 7, we will say, but what if we have 3, 4? How do we decide what is most, right? Because maybe 3 of these 4, and 3, we need some computational or mathematical notion of what it means that this a question divides the sample best according to the labels. Okay, this will be the thing we will try to find, or one idea, or what I'm going to show is one way to do that. As I said, there are other ways of doing it, and depending on the data, they can work differently. What I'm going to show is one of the more popular ways for decision trees. So this is what we're going to talk about, or the method that I'm going to show for selecting the best attribute is based on something called information theory. Information theory means how much information is encoded or given by a specific data. And again, we'll get later to that, but you can also take it to conditional information and so forth. But before, let's just introduce a notion of information theory, which is called entropy. Entropy is a notion that was borrowed from physics, but was applied to information theory. And entropy basically covers or tries to determine how much information do I need to send you in order for you to know an outcome, okay? So just as an example, if I flip a coin that always falls on heads, okay? And I want to transmit to you what is the outcome of my coin flip, then I don't need to send you anything, because I could flip the coin, it's going to be heads, then the answer is 0. I don't need to send you any bit. However, if I flip a fair coin, right, which can be basically 0 or 1, heads or tails with equal probability, then if I need to tell you what is the outcome, I need to send you the bit, right? 1, let's say, for heads, and 0 for tails. Otherwise, you wouldn't know what I had. So this is entropy. Entropy tries to quantify the amount of information I need to send to you in order to communicate something that you might know something about. Okay, so maybe you know that this coin is 70% heads and 30% tails. How many bits do I need to send you? Okay, and entropy is defined as this function here, minus, so x is the random variable, let's say a coin or a die or whatever, and p is the probability, and c is the set of values that a random variable can take. So it could be heads or tails, so c will be heads and tails, or if it's a die, it could be 1 to 6, or if it's I don't know, a director, it could be 4 values and so on. We have a probability, and this, and then it's just the product of the probability times the log probability. So let's see how this looks like for a binary variable. So for a binary variable, if the probability of x equals, let's say, in this case, this is the probability of, so this is the entropy, and this is the probability that x equals 1. So if the probability that x equals 1 is 0, right, it means that x will always be 0. This is a random variable, a binary random variable. If the probability that x equals 1 is 0, then x will always be 0. If x is always 0, then I don't need to send you any information for you to know what x is. Again, let's say 0 is heads, and 0 is tails, and 1 is heads. Similarly, if the probability of x is 1, then I don't need to send you any information, because because the outcome is known. You know already that it will always be 1. On the other hand, if the probability of heads is half, then when I flip a coin, you have no idea if it's heads or tails. I need to send you 1 bit to tell you that this is basically, so this is basically the outcome that I got, right? So h of 0.5 in this case is 1. If the probability is half, it's 1. If the probability is 0, it's 0, and if the probability is 1, it's 1. Okay, so this and this, if you just plug in the numbers, you will see that this comes out, right? If the probability is 0.5, then, right, minus P of x times log P of x is going to be 1. And by the way, anything, again, for those who are keeping track of math, anything multiplied by 0, we denote as 0. So even if there is a log of 0, which is undefined, this will still be 0. Okay, so we are treating it as 0. Okay, but anyway, this is the entropy. You know, one interesting thing about entropy, for those who haven't seen it, as most of you have seen it, but one interesting thing about entropy, for those who haven't seen it, is what happens when the entropy is not 0 and not 1. So, for example, right, so we know that if the entropy, if P of x equal 1 is 1, then the entropy is 0. If P of x is 0.5, then the entropy is 1. But the interesting thing may be what happens when the entropy is, or not the entropy, the probability is either between 0 and 0.5 or above 0.5. In that case, what this tells you is that the entropy is between basically 0 and 1. It means that for any coin flip, I have to send more than 0 bits, but less than 1 bit in order for you to know what the outcome of my coin flip was. But how do I send 0.7 bits? Or how do I send 0.3 bits? Okay, so the answer is that you don't send 1 bit, you send multiple bits. Here is an example. And again, this is just to understand what entropy means. We won't really use it, but it's good to know because we will use it. We will use the entropy, so it's important to understand how this relates to the information. So let's say that P of x equal 1 is 0.8. Okay, so it's not 0 and it's not 1. If that's the case, then rather than encoding 1, of course, if I need to send you every coin flip I did, you do not know if it's 1 or 0, right? It's not going to be completely always 1 or completely always 0. But so if I send you every coin flip, I will have to send you 1 bit per coin flip, and then the entropy will be 1. But we know actually that for 0.8, the entropy is not 1. So how do we reduce the number of the bits that I have to send? The answer is that we don't encode every bit on its own, every coin flip. We encode every pair of coin flips. So specifically, if I have heads and heads, okay, so the probability of heads is 0.8. If I get heads and heads, I send you a 0. So I flip the coin twice, and then I send you the outcome. Okay, if I get heads and then tails, I send you 1, 0, tails and then head, I send you 1, 1, 0, and 2 tails, I'll send you 1, 1, 1, 0. Okay, so this is the code I'm going to use. You will know when you get a 0 that I sent you 2 outcomes, right? Because if you get just 0, you know that I had 2 heads. If you get 1, 0, whenever you see a 0, you know that that's the end of my 2 flips. So it's not hard for you to parse this message, okay? But the question is, how many bits do I need in order to send this to you? It seems like, right, rather than sending 2, sometimes we send 3 or 4, right? If we just send 1 for each one, we'll send 2. But now we may send 3 or may send 4. What did we gain here? The answer is that even though we can send 3 or 4 sometimes, this is very unlikely, because this requires that we will get either 1 or 2 tails, but this doesn't happen a lot. So let's see what's the expected number of bits I'm going to send in this case. Right, so let's say that I got this outcome. So I have tail, head, tail, tail, head, head, tail, head, and so forth. So I'm breaking it into 2, and this is what I'm sending you. Okay, so this is just an example. But what's the expected number? The expected number is going to be the expectation for 1, 1, which is 0.64, times the number of bits that I'm sending, 1, plus the expectation of 2, of 0, of 1, 0, expectation of 0, 1, and the expectation of 0, 0. So overall, even though I may send sometimes 4 bits and sometimes 3 bits, the expected number of bits I'm going to send is actually lower than 1, right? 1 is the default if I send for every coin flip. And in this case, the expected number of bits is less than 1. By the way, I'm dividing it by 2 because this is the expected bits per flip. And I'm sending this for every 2 flips. So I'm dividing this by 2, okay? And this is what I'm sending for each pair, right? So if the pair that I got was 1, 1, I'm sending 1 bit. If the pair that I got was 1, 0, I'm sending 2, and so forth. So what I'm getting is 0.8 bits on average per coin flip. So this is less than 1, right? So if the probability of 0.8 or if the probability of a coin flip is 0.8, then the expected number of bits is, or in this method, is 0.8. The entropy, by the way, of 0.8 is 0.72. So this is slightly higher than the entropy. Anybody can tell me how we get closer to the entropy? So I gave you an idea that sends pairs or the outcome of pairs, and this got us to 0.8. How do we get down to 0.72? Anybody? Raise your hand, or you want to write it? Yeah. So So I guess the answers. So increase the number of. Well, more efficient encoding for 2 is very hard to do. There's no other way to encode 2 because you need to send the 0. You have to have the 0 at the end. Otherwise, the receiver, because you send you don't send just 2. If you just send 2, that's easy. But you send basically a stream of 2. So you have to have something that the receiver will know. That's it for these 2. So the answer, and a lot of you answered this, or at least meant, some of you actually said it, some meant, I guess, is that, we can extend this to, rather than sending every 2 bits, every 2 flips, we can do it for 3 flips, or for 4 flips, or for 5. In fact, at the limit, we'll get to 7.2, but 4 or 5 will already get us very, very close to 0.72. So rather than sending every pair of flips, we can send every 3 flips, every 4 flips. Again, some of these will be very long, but the probability of saying 0, 0, 0 is very, very low. So even if we send a lot of bits for that, the expectation will be low. So in order to basically reduce further the expected number of bits, we can go to longer and longer. However, the entropy is the lower bound. Even if we go to 1 million, we will not go below 0.72. So we will always need at least 0.72, whatever the entropy is. So that's a lower bound on the information. Okay, so this was the idea of entropy. And it's related to how much information is already provided by knowing the distribution, right? I mean, the advantage here is that we know the distribution. So this is the entropy, or we gain advantage by knowing the distribution. Now we are going to introduce another concept, which is called conditional entropy. Now, conditional entropy, is a fancy word to say entropy restricted to a subset of the information. Okay, so if we look at this outcome here, this is the label, right, that we are trying to predict. If you look at this label, it's 60%, no, it's 2/3 yes, right? So we have 6 yeses and 3 no's. So 2/3, third. So you can ask, what's the entropy of the label, right? We can just compute the entropy. It's like 2/3 and 1/3, and we can go to the tail. We can go to this place here. So basically it's 1/3, roughly maybe here, and the entropy is something like this here. Okay, so maybe 0.9 or something. That's the entropy of the label. So we can just go to the label and determine the entropy. However, we can also do something called conditional entropy, and that is compute the entropy for the label, but restricted to samples that have a specific answer. For example, I just want to compute the entropy of the labels if the movie is long. In this case, let's say short. Okay, so if we just look at the entries in the table where the movie is short, this is short, short, and short, then it's still 2/3 and 1/3, but I guess some others wouldn't be that, right? Or maybe in this case it doesn't change. But anyway, we can actually compute the entropy for the subset of the samples that have this value. This is conditional entropy. That's it. It's not, there's nothing fancy here. We just compute the entropy of the, in this case, of the random variable, or the variable that we treat as the label, conditioned or restricted to the set of entries in the table that have a specific value for this feature, for this question. Okay, I will show you an example. So for example, if I want to do the conditional entropy of light condition on short, then I'm just selecting the rows for short. These have 3 values. So once I select short, of course, everything is short. These have 3 values, and then it's 2/3 and 1/3, right? So the entropy is going to be 0.92. And I can do it for them, right? For medium, for example, I liked all the medium movies. So the entropy for medium is 0. And the entropy for long is also 0.92. Okay, so now I can compute the information that I have for the label itself, which is 2/3 and 1/3, but I also can compute the information that is provided to me, or the amount of information that I had from a subset of the samples that are identified by a specific answer. For example, how long is the movie? So if it's short, it has this entropy. If it's medium, it has this entropy. Okay, this already gives us some clue about what type of questions we should ask, right? Because the lower the entropy and the conditional entropy, the more informative the question is. Because if the question leads to a very low entropy, all the labels are going to be the same, right? That's the idea of the entropy. Okay, but unfortunately, or not unfortunately, this is good for conditional entropy, but the question is, how do we get the entropy of, we don't want to ask what's the probability or what's the entropy given short. We want to ask what's the entropy given this question. So the question is on the movie length. So we need to somehow sum up all of these individual conditional entropies and get one value, which will be the value for this question. And then we'll get one value for another question and for another question, and we'll choose the best question. So how do we do it? We can actually combine the conditional entropy now, not on a specific not on a specific subset, but on a specific questions by writing the entropy of y, which is the label given x, which is the specific question, as sum over I, summing over all the possible answers to the question, the probability of that answer, and the conditional entropy of the label if this is the answer. Okay, so this is a way to combine, this is called conditional entropy, and this is a way to combine all the possible answers to a specific question. Right, so we have all of these labels, or basically we have all the possible questions for all the possible questions for our all the possible answers for movie length, and we want to basically combine them into one value, which tells us how good is this question. And this is done by basically weighting how many samples have this answer, and for each of these answers, multiplying that by the conditional entropy that we get. Okay, so this is just a way to sum the conditional entropies for a specific question. Okay, and we can do it for any question, right? So once we know how to do conditional entropy and sum over all the possible answers, we can do for any of the questions. So this is, right, how to compute h of y given a specific answer we know how to do. We just select short, short, and short and compute the entropy. And the probability of x is just, again, using maximum likelihood, we can just see how many times we see short divided by the total number of times, and this is the probability. So if we are doing it for this one, we can compute the conditional probability of the label, okay? So conditional entropy of the label, which is the value we want to transmit, or the thing we care about, condition on length. And here I'm not using any specific answer, but on the question of length, okay, which is what we want, right? We want to find the conditional entropy on the question that we can ask. So the conditional entropy of the label on the length is just a summation over the conditional entropy of each of the answers times the probability of that answer. And if we do it, we get 0.61. Okay, so this is just the logs. Now, of course, we can do this for any of the questions, right? So this is one question, but we also have a director, and we have famous actors, and we have other things. We can do it for all of them once we do that. Once we have that, we can compute the final quantity that we will need for this class or for determining the best attribute, and this is called information gain. Information gain is the difference between the entropy and the conditional entropy. So the entropy is what is the entropy, or how much information do I have if I just know the label. So I know the distribution of the label. How many bits do I need to send you about whether I like the movie or not if you just know that I like 2/3 of the movie and then it's like 1/3? Okay, this is the entropy of my my Y value. Okay, so this is how many bits do I need to send you to tell you whether I like this movie or not, given that you know that I like 2/3 of the movie and didn't like 1/3. Conditional entropy is, as we said, if you knew not just the distribution, but you also knew the distribution for a specific question. So basically, you know, in addition to the labels, you also know whether I like this movie or not. So you know the distribution for each of these, and you know the value for the specific movie that I want to send. So this is called information gain, the difference between the entropy and the conditional entropy. We denote it as IG of Y and X, and it's always positive, or not positive, but it's always a non-negative. And this is something that you will prove in the problem set. But for now, or for this class, we will assume that this value is always non-negative. Okay, so it could be 0, but it could also be a positive value. Okay, and again, this is something new. Okay, so this is called information gain. And information gain basically is what we are looking for. So remember, we are looking for a criteria for the best attribute. We defined entropy, conditional entropy, and now we came to this notion of information gain. Information gain basically quantifies how much each of, we basically do it for each of the questions, but it tells us how much each of the questions improves on what we know now. So we are at a specific stage in the tree, we have these samples, and now we want to know from the set of questions that we can, some questions we already asked, so we cannot use them anymore. But so questions we did not ask, we want to know which of the questions provide the most information on the label given the set of samples that we have. And that answer is the one that maximizes the information gain, because this is the entropy of the current set of samples we have. This is the entropy after we know the answer to a specific question, and the difference is the gain. How much information do we get from asking this question, or from knowing the answer to this question, with respect, of course, to the label. So this is called information gain, and this is what we will use to find the best attribute, or we will look for attributes that maximize the information gain. Okay, so let's do an example, or let's. So as I said, so one, I mean, that's not the only way. As I said, there's lots, because this is a greedy algorithm, there's lots of ways, but one way to find the best attribute is to use the information gain. So let's do an example, right? Remember, we want to classify this data set. So we have a set of movies, we have the type of the movie, the length of the movie, the director, famous actors, and finally we have the labels for each of the movies. Okay. Now we can compute as I said, the entropy of the label, and the entropy of the label is 2/3 and 1/3, so the entropy is more or less 0.91. And we can also compute the conditional entropy for each of these questions, and if we do that, you see that for type and for length we have 0.61, for famous actors it's 0.85, and for a director, it's 0.36. So now we compute, so this is the conditional entropy, and now we can compute the information gain. And we see that the information, the biggest gain we get is when we ask a question about the director. This is, of course, applied to all of the samples, and when we ask using the director, we get a very low entropy, conditional entropy, and a very large information gain. So this is going to be the first question that we will ask. Okay, once we identify the question, we just build the tree, right? We go to the recursive function, we say all samples that have this director go one way, all samples that have the other director go this way, and all samples that have, in this case, we have 3 directors, they go to the 3rd way. Okay, so this is the first question we ask, and how we divide the samples. So all samples with single will go to this side, All sample with Elastitor will go here, and all sample with Arboretum will go here. And now we basically take all these samples and run again the algorithm, and we see that all of the Adamson samples, I like their movies. All of the Singer ones, I also like them. So we are stopping, right? We said if all the labels are the same, in this case, yes, we stop. For Elastitor, I have some that I liked and some that I didn't like, so I have to continue with the algorithm and identify another attribute, and again, do the same recursive call. So here, we don't know, and we need to find a new question. How do we find a new question? Before we ask a new question, we do two things. First of all, we just take the samples that are assigned to Elastitor, right? We don't care about the ones that have Singer and Adamson anymore because they go others. We just care about some of the samples that have this answer to this attribute, right? This is the set of. The other thing is that we are going to remove from the attribute list the director, because we know that all the samples here have the same director, so it's not going to help us. So the input to this recursive call is going to be this part, okay? So this is the new input that we are going to use. We removed all of the samples that have a different director, and we removed the column on the director because we know that all the samples here have the same director. That's not going to be a useful question for us. And now we have still 3 other questions that we can ask: type, length, and famous factors. And we again compute the same thing. So we compute the entropy, we compute the conditional entropy, compute the information gain, and in this case we have 2 possible questions that lead to maximal information gain. We take one of them. Let's say we use the type of the movie. We ask this question about the type, and because we know that this will lead to 0, then this will be a perfect solution. Okay, and this is the final tree. In this case, once we have all, so we don't have any more internal nodes, everything is assigned to a leaf, or everything is a final, a terminal node, we are done. And now if a new movie comes in, or if a new sample comes in, we ask which director, and then we ask which type, and then we make a decision, or maybe just later. Okay, so this is the final tree that we obtain, and this is the end of the algorithm for this. Okay, right. So any questions on this? On decision trees? I don't know if anybody has some general questions before we move on. I mean, we didn't finish decision trees, but we did finish the basic learning algorithm. Okay, nobody has more questions. I guess Daniel answered some of your questions. So let's continue.
One just popped up now, like what about pruning?
Yeah, so we'll get to pruning in a second and explain what pruning means and why we need it. Okay, yeah, so this is the basic algorithm, right? And this is the final tree. This is the final tree, and if you look at the samples, you will see that this tree gets everything correct, which is not a big deal, but it's nice to see that it will always, all of the questions, all of the samples will be correctly classified. Now let's get to something called pruning, or something called overfitting. So if we have a big enough data set, so if we have a lot of questions to ask, then even if some questions are not really relevant, they are just noise, we may eventually use them because they are useful for us to separate yes and no things, right? For example, let's say we want to predict whether someone, or we want to predict whether someone is a male or a female, and we are using height and weight, right? So height and weight are definitely not enough to classify male and females. So let's say in addition to height and weight, I also give you information on things that are completely unrelated to gender. I don't know, maybe which book you have now on your shelf, or I don't know, things that are, or what color. I mean, anyway, let's say that we have questions that are completely, what time did you enter the building today? Or what time did you enter you opened your computer today? Or things that are really independent of anything related to gender. Because if we have enough samples, then it will be the case that some of these questions, even if they're not related, will lead to slightly better separation of the labels based on just not using these questions, right? And what we said is, if anything leads to information gain, we are going to use it. So this will mean that in the tree that we are going to generate, we will have a lot of questions that are completely irrelevant to the classification, but we are using them just because we don't have any good questions anymore, and we are trying to, and we are splitting based on some basically noise in the data. This is dangerous because this can lead to something called overfitting. Overfitting means that the algorithm will work very, very well on the training set, but it will not work very well on a real set, right? Our goal of machine learning is not so much to have a perfect solution for the training set. It's really to generalize to an unseen set of data, right? If Netflix is going to use your algorithm, they really want to ask the questions that are relevant to the solution. They don't want to ask questions that are just completely independent of any result. So this is called overfitting. And we will talk actually a lot about overfitting in a lot of classes. For example, when we talk next time about linear regression, or when we talk about logistic regression, there's something called regularization. There are other ways to do it. In decision trees, usually overfitting is dealt with by something called pruning. Pruning means that we build the tree, okay, and the tree we think contains some relevant questions, for example, height and weight, but it also contains non-relevant questions. So after we build the tree, we remove some of the questions. How do we know how to remove questions? One way to do it is using a test set, okay, like we did when we started the tree. So basically, we start with a tree. Oh, sorry, not start with a tree. We start with a training set. We take, let's say, 75% of the data of the samples. Let's say we have information on 1,000 movies. Okay, so we use 800 of them to learn the tree. We know, and we learn the tree like we said before. So basically, we ask all the questions we can ask. We don't know if this question is noise or not. There's no idea. So we just take the ones that lead to best information gain, and we go all the way down until we can't ask any more questions, or until, as the algorithm says, everything has the same label. So now we know we have a tree, and we think that this tree contains some overfitting, some questions that we shouldn't ask, but we don't, of course, don't know which ones. If we knew, we would remove them. So now we take the test set and use that to prune the tree. Basically, prune means removing questions from the tree. How do we do it? We take the test set and we compute the accuracy of the test set based on from the top to the right. So we see if the prediction using the first question improves on the values for the test set. Let's say the test set has 50% like and 50% didn't like. So we ask the first question, and we see that the first question identifies 60% like, 40% not like, and the other part 40% not like. And so this is better than what we had in the original test set. So we continue, right? And we go on and on and on until we get to a question where actually asking this question makes our prediction on the test set worse than without this question, right? Because at any node we can stop and say, okay, take the majority and this will be your result. And let's say the majority is 70-30, so we will get 30 wrong, but 70 correct. If I ask this next question, I actually may change that. I may actually get to 80 wrong and 20 correct. Okay, so that's when I stop. So and then when you see that the next question is going to deteriorate your result on the test set, you stop, you remove this question and all the questions below that. So all the subtree rooted at that location. So, but that's very important to start with the top, the most important question, the most relevant question, go down, down, down. Each time, of course, we are just using the samples that are associated with this question because some samples go this part, some go. And then at some stage we say, okay, this question is actually going to make or going to work worse on the test data compared to not asking this, so I'm removing this subtree. So this is called pruning, removing subset of the trees. And it's very useful thing to do. There are other ways, more crude ways to do it. For example, you can say I only want trees of length 3, of length 4. I'm not going to ask more than 4 questions in a row. Okay, that's another way to do it. Usually not something we do in decision trees themselves, but it is something we do when we combine decision trees with other methods. So we will talk later in the class about maybe about something called boosting. In boosting, again, we didn't talk about it, so you don't need to know what it is, but boosting sometimes uses a lot of decision trees, but each of the decision trees it uses is very short, maybe 2 or 3 nodes, that's it. So that's another way to limit overfitting. The problem is that, of course, this requires you to combine a lot of trees. If you just want to use one tree, this will. Okay, so this is the idea of pruning and avoiding overfitting, very important point. Another point that we didn't cover is continuous values. So let's talk a little bit about continuous values. Let's say that we want to predict male or female in this class from a height, okay? And let's say we have a very, precise measure of the height. So it's not just, I don't know, 5'8", but it will be 5, 8, 7. So we get really 10 values after the decimal point, or really, really continuous values, okay? So now, and our goal is to build a decision tree with this information for male and female. Can we use information gain for this? Anybody can tell me if we can use information gain to determine what value we should use to ask the question? Right, so I want to find the question. So basically the question will be a binary question, whether you're more than 5.8, I will say this side, and less than 5.812, I will go to the other side. Is there a way for us to actually use information gain in this case? Or is there a problem with using information gain in this case? So again, right, we have let's say now we have 92 students listed. I get the height from each of you, and I want to find the question that will lead to the maximum information gain where the label is male or female. So integration may work or may not. I don't know exactly how integration would help here. Good. So now Jacob is getting to the right solution. So the answer is, surprisingly, or maybe not surprisingly, that you can use information gain here because the number of samples is discrete. What we can do is we can order the sample based on height. The number of questions we can ask, of course, is infinite, right? Because we can ask 5.8 to 7, 5. But most of these questions will lead to the same information gain. Because if the question is not between two individuals, right, any value between two individuals will lead to exactly the same division if I'm ordering the samples. So what we can do is order the samples, we have 92 here, and consider 91 questions. Each question will just divide the class into 2 groups, right? Maybe 1 and 91, 2 and 90, and so forth. Each one will lead to a different information gain, and I'm choosing one of them. So the answer is you can actually do or you can compute information gain even for continuous values. At least for the training data, it's going to be, of course, there's infinitely many, but effectively they will lead to the same information. A lot of them will lead to the same information gain, because if the value is between 2 individuals, it doesn't matter which question you ask, you will get the same separation. So what we usually do for continuous values is we can order them and then just look at the midpoint between any 2 ordered points and compute the information gain. So this will work. So basically, you can use information gain for, of course, it will take more time because unlike before, we have maybe 90 questions that we may want to ask. But still, this is doable, and it will actually work reasonably well also on the test set, because usually there's not a lot of differences between individuals. So that's good. And so basically, whatever we talked about now can be used for continuous values as well. Usually, and of course, you can do it for more than 2 questions. If you do more than 2, that becomes exponentially, or the number of things you need to measure. Let's say you want to ask 3 questions. So whether you are more than 5.8, between 5.8 and 5, and less than 5, right? You can ask 3 questions, right? We said that, of course, is exponential in the number of questions you want to ask, because you need to now divide them into 3 groups, 4 groups, and so forth. So there's going to be a lot of them, but it can actually. I remember even that. Yeah, I think we used to ask about this in the problem set. Yeah, right. So it's not going to be. Right. So, Yeah, you will need to, right, it will be exponential. But anyway, this can be done. But what's the difference? So this works well for discrete and for continuous values. So that's not a problem, information gain. What's the difference between continuous values and discrete? There is one big difference between continuous values and discrete in this case. Anybody can tell me what's the big difference? Or what's going to be a big difference? Based on the algorithm that I showed you. So basically for continuous, we can, as I said, we can still use the find best attribute to find, but one thing in this algorithm is incorrect if we use continuous values. What is it? Exactly, right. So I don't know who is Setong Lu, but she or he answered correctly. Unlike discrete, remember in the discrete we said, once you use a question, you cannot use it anymore because everybody has this answer. Right? If I ask this director and I'm dividing based on the director, everybody is going to have the same director. So there's no way for me to use it again. In continuous, that's not true, right? So I can say, okay, if you are more than 5.8, you go 5.8, you're going here. But then I can redivide it again. And actually, this could lead to better results if I divide one of these two again, right? So maybe, right, maybe I'm asking two questions. So I'm only allowed to ask binary question, whether we are more than 5.8. But then between 5.8 and 5, you're one, and less than 5, you're another. That's a valid question to ask. So unlike in the discrete case, when we use the continuous variables, we are not erasing it. We can still use it again and again and again. Of course, this can lead to overfitting, but we can use it again and again in the tree, even if we used it already once. Okay, that's a very big difference between continuous and discrete variables. Okay, so let's go back. Yeah, so we talked about pruning. Right, so we talked about pruning, we talked about continuous variables. Now I'm going to show you some interesting results. Maybe not that interesting. They are not. So several years ago, neural networks were not as successful as they are now today. We will get to neural networks. You will learn about the revolution that happened in neural networks. Basically, the real revolution in neural networks is the fact they became deep. That's the big deal. But deep meant a few things. So it meant that, and again, there will be a lecture, so you don't need to understand if you are not familiar with this, but deep meant that we needed much more computing power, we needed much more samples, and we needed better algorithms. So it wasn't just saying deep and that's it. I mean, there was a lot of things that had to come together for neural networks to be successful. But until 10 years ago, 15 years ago, for sure, the people have used neural networks for decades. Again, this will be covered in the neural network, but neural networks have been around from the 60s. So it's not a new classifier, but it wasn't as good before. 15 or 14 years ago, researchers, and this has not been, that's why I'm not showing you new results. This has not been, I think, nobody tried it recently. But people try to find what is the best classifier. And again, in this class, we are going to cover a lot of different classifiers. At the end of this class, you will know a lot of different classifiers. And a question that always comes up is, which classifier should I use for my data? And the answer is, we don't know. Really, that's why we cover a lot of classifiers. Some classifiers work good for one data and another classifier works good for another data. Usually people in different domains know about it. As I said, in the sciences, people really like to use decision trees, not because they work so well, but because they are very interpretable. In image analysis, we know neural networks work very well, but nobody proved that they are the best. So the answer is we don't really know. So some people, or at some stage, people started to do some meta-analysis, taking a lot of different classification problems and trying to see on average which classifier, so if you don't know anything about the problem, which classifier should you use? Okay, this is from 2006. So I'm not going to, my goal is not that you read too much into the ranking here because the ranking changed completely, especially neural, specifically or mainly neural networks. The other algorithms here, and I will mention them, did not change dramatically over the years, but neural network changed a lot. So here, this is artificial neural networks. I wouldn't read too much into it. But this is the ranking of the methods without, and if we ignore neural networks, all the other methods did not change since 2006. So Of course, the data sets may have changed, they're much bigger now and so forth, but generally speaking, this is an interesting ranking, or at least something to consider. Now, if you look at this ranking, so the top one is the best and the bottom one are the worst. If you look at this ranking, you see that naive Bayes in general doesn't work very well. And we talked about it. It makes very strong assumptions about distributions and about probabilities, and that's not true. Logistic regression doesn't work very well. We haven't gotten to logistic regression, but it's important to understand because logistic regression is basically something that we use a lot in neural networks. So even if you don't like logistic regression, or even if you think based on this slide that logistic regression is not important, I highly encourage you to try to understand logistic regression because we will use it a lot, or it's a component within neural network. The next thing is decision trees.
Zip, there's a quick question here. Someone said, how would cross-validation work for pruning a decision tree? Because each fold would give you a different tree.
Yeah, so cross-validation, okay, good. So let me answer that quickly. So when people use cross-validation in decision trees, usually what they do is they do it on levels. So they are not doing like the pruning idea. They ask, basically they compare different levels of trees. So I'm allowing you to ask 5 questions, 6 questions, 7 questions, and they compare the number of questions. They don't compare the tree itself. Once you finish the cross-validation, you relearn the tree from all the data, but only limiting to the length that was determined by the cross-validation. So that's usually how people use cross-validation with decision trees. I agree, the same tree itself wouldn't work in this case. So pruning is good, but it's only a trained test. If you want to use cross-validation, usually you do it based on levels. So you do 5 levels, 6 levels, 7 levels. And stuff. Let me go back 1 second to this table. So this is k-nearest neighbor. K-nearest neighbor as a standalone algorithm is not doing very badly, but it's not great. Neural networks back then, as I said, caveat, the best algorithms that we will cover in this class is support vector machine. Okay, so this is the standalone algorithms. But if you look at the top 7 algorithms here, BEG-DT, RF, I mean, BST-DT, whatever they mean, these top 7 algorithms are all decision tree algorithms, but they are not using decision trees on their own. They're using something called ensembles of decision trees. So this is called the Begin decision tree. This is random forest. This is boosting decision tree. I mentioned boosting. We will not cover it. But the best algorithms back then, and still this is true today, are methods that use decision tree, but don't use decision tree on its own. They use something called ensemble. They use a combination of decision trees. Okay, so how do we combine decision trees? How do we use decision trees multiple times? It's a bit of a problem, right? Because decision tree is not a probabilistic algorithm. If I learn a decision tree again after I learned the first one, I will get the same decision tree again, right? I mean, this is what we showed is a deterministic algorithm. So if we want to have a combination of decision trees, we have to inject some randomness into the process. Otherwise, we can learn 20 decision trees, but they will all be the same. Any ideas of how to inject randomness into learning decision trees? Anybody has suggestions on how to do that? Again, people understand the question. Let's say I want to learn a lot of decision trees and take the majority vote, for example. That's a good idea, right? I learn 10 decision trees. I take each sample, I use each one of them separately, and then I take the majority vote. Good, yeah, so EHO basically provided both answers, and both of these have been used. One is to use a subset of the data. So rather than learning one tree from all the data, let's say we take 90% of the data, learn the tree, and then sample with replacement, of course, another 90%, learn the tree, another 90% learn the tree, and so forth, and basically we will use this tree. This is called Begin decision trees, and I'll show a bit more formally in the next lecture. The other idea is take a subset of the features. Now, this is a bit more dangerous because we don't know which features are useful and which are not, but you can actually do it and select a subset of the features. So not all the features, and of course the question is how many. There's some there's no good theory, but there is some practice related to that. And basically you select a subset of the features, you learn tree just with that features. Then with replacement, you select another feature, you learn another tree and so forth. And you combine these trees. This is called random forest. So the first one, selecting a subset of the samples, is called begging. The second one is called random forest. And again, next time I will go over these a bit more formally. The third idea is something called boosting, and again, we haven't talked about it. We'll have a complete lecture about it, but this is a completely different idea, and that idea is rather than selecting a subset of the samples or selecting a subset of the features, place different weights on different samples in each iteration. So basically, some samples are more important in one iteration, and some samples are more important in another iteration. Of course, if that's the case, then the trees can be different. Exactly how to do it and how to combine it, I'm not going to discuss this. So next time, this will be left to another class, because this is a large set of methods called boosting. We'll get to that. But I will discuss a bit more formally next time, bagging and right. So how to combine the tree and how to use them, I will talk about this for a bit more in the beginning of next lecture. Okay, so we're out of time. But these ideas of ensembles of trees, the important thing I think to mention is that even though decision tree on its own doesn't usually work very well because it's just one tree, ensembles of trees are great. They first of all work very well, and second, they are still interpretable. We can still understand a lot of the decisions they're making. We can still understand the questions. They can still be used with your collaborators if you're working in the sciences or with people who are not experts in machine learning and still understand what they're doing. So don't give up on decision trees, even if they are very simple, okay? So that's basically it for this lecture. As I said, next time we will move to regression. I will cover a little bit the ensemble methods in more detail. And of course, boosting will be a separate lecture later, which will cover some of this and some. And that's basically it. I'll see everybody on Monday.